Alright, today we're going to start in on Unit 9, and we're going to group 9A and 9B together into one section. There's going to be a couple different videos, and we're going to start talking about what's called stoichiometry and lots of math in this section in stoichiometric calculations. Now, before we talk about the specifics of stoichiometry, I want to introduce the idea of proportional relationships, and this is what we're going to be dealing with throughout this entire unit. And up here is a recipe for chocolate chip cookies. And this recipe, we start with this because everyone has seen recipes before. They've all made them, even if it's pretty simplistic. And you've got your flour, your baking soda, salt, butter, sugar, etc., etc. But more importantly, it gives you amounts that you need in order to successfully make this batch of cookies. So for example, if I have 5 eggs and I have plenty of everything else, okay, I have lots of flour, lots of baking soda, lots of butter, lots of chocolate chips, everything else. But if I only have 5 eggs, how many cookies can I make? Now, some of you are already doing the math. Okay, 2 eggs are 5 dozen cookies, so I can definitely make 5 dozen. I've got 4 eggs. I can definitely make 10 dozen. And you're right. Totally get there just doing simple math. I'm going to show you how we would calculate it from a chemistry perspective and then be able to explain it. So we start with 5 eggs. And we're going to treat this recipe like a balanced chemical equation, and then it's going to give us ratios. Okay, so for example, I would think of it as 2 eggs and all my other ingredients, my, 2 1/4 cup flour. But then my product is going to be 5 dozen cookies. So I can look at this like a ratio. So if I say, and use it as a conversion factor, which I know is not everyone's favorite, but that's what we're going back to. So for every 5 eggs, I make 5 dozen cookies. So I put the eggs on the bottom, because that's the unit I want to cancel out. And I put the 5 dozen on top, and then I do the math. I take 5 times 5, and I take 5 and I divide it by 2. Cross those off. So I end up with 12.5 dozen cookies. Okay, now we can have a discussion about whether or not you actually make that many cookies, depending on if someone eats the dough or if you make your cookies uniform size. But if we were to follow the recipe, in theory, we could end up with 12.5 dozen cookies. And if that makes sense, if you understand recipes and ratios, that's essentially what we're going to talk about in this unit, just with moles and grams and chemicals and all that stuff. So there's our ratio of eggs to cookies. Okay, now let's talk about stoichiometry. Okay, keep a color scheme. Stoichiometry is defined as the mass relationships between substances in a chemical reaction. Okay, chemical reaction. And it's all based on mole ratios. Okay, mole ratios. Now, a mole ratio is simply indicated by the coefficients in a balanced chemical equation. So there isn't funky new stuff to this. It's just coefficients in a balanced reaction. So you have 2 magnesiums for every 1 oxygen for my reactants, but I also have this ratio of producing 2 moles of magnesium oxide on the other one. So the coefficients here are going to give us our ratios. So we have 2 magnesiums, 1 oxygen, and 2 magnesium oxides. And you're going to see how we're going to use that in order to do some of these math problems. Okay, now the term stoichiometry is ugly, looks ugly. It comes from the Greek word stoichion, meaning element, and metron, meaning measure. Okay, so in essence, you're just measuring elements, and that's exactly what we're doing. We're measuring the relationships and the ratios between these elements and these compounds. Now, we will talk about compositional versus reactional stoichiometry, and we've done compositional stoichiometry. These are things like, come back here. Compositional stoichiometry are things like percent composition, when we found empirical and molecular formulas. So this is when it's static, when you're simply using the ratios of a compound to figure out what percentages different elements, as well as figure out the formulas. Reactional stoichiometry is when we're going to use a balanced chemical equation. Okay, that's what's going to be the difference here. Okay, we are all going to come back to what is known and what is unknown. So we're going right back to always figuring out what they tell us, what we're trying to figure out. And we have to be able to use a couple of old, not old, but different conversion factors. Now, the big conversion factors that we're going to use are going to be molar masses. Okay, so you've got the periodic table. Remember, you find the molar masses. For example, if we had water, if you go to the periodic table, hydrogen's molar mass is 1.01. There's two of them to get me to 2.02. Oxygen, there's one of them. Oxygen's is 16.00. So we end up with 16.00. We would end up with 18.02 grams per mole, and that's how we find molar masses. Okay, same way we've been doing that for a long time. If you need to go back and rewatch some of those videos, feel free to do that. And then the mole ratios, which we talked about from the balanced chemical equation, when we just had 2 magnesiums plus 1 oxygen gives me 2 magnesium oxides. Okay, that's where those coefficients are coming from. Now, some old math we cannot forget, and it's going to come back pretty hard right now. One is our metric prefixes. We'll do a little bit of math review on this stuff next unit, but things like kilo, milli, pico, nano, all that good stuff. All of that's coming back, and it's all you're gonna see it a lot, so make sure you review that stuff. And last but not least, we also should remember Avogadro's number. That's not going away, even though we'd like it to, which is 6.022 times 10 to the 23rd. Molecules are atoms per 1 mole of a substance, or atoms. Okay, so again, we're not adding any drastically new math. Remember, I kept warning you we were eventually going to go from one substance to another. This is it. So all this stuff is going to come back pretty hard. So if you're not sure, you got to get in and ask questions so that we can get you caught up. All right, so let's do 2 samples. If I have a reaction that begins with 13 moles of aluminum oxide, how many moles of aluminum will be created according to the following reaction? All right, I'm going to put my known and my unknown up here. I start with 13.0 moles of aluminum oxide. My unknown is how many moles of aluminum. Okay, now I want to go from moles to moles. So in order to go from moles to moles, the only thing that I can use is the mole ratio, and that's going to come from the balanced chemical equation. So the two that I'm looking at are aluminum oxide and aluminum. It didn't ask me anything about oxygen, so I don't need it, so I'm just going to go ahead and cross it off. You're going to see we're going to keep using the same reaction over and over and over again. Now this one, I gave you the balanced chemical reaction. There also will be questions where you're asked to write the reaction first and then answer questions based on it. So the naming is not going away either. It keeps building on itself. So how do we set this up? Well, we still always start with what we're given. 13.0 moles of aluminum oxide. All right. Okay, I've got 13 moles of aluminum oxide. I want to go to moles of aluminum. Remember, it's all the way back to what I want to go to goes on the top. What do I come from is on the bottom. So my moles of aluminum is on top, and this is where the number comes from. It's simply 4 moles of aluminum. It's that recipe. It's that chemical recipe. So 4 moles of aluminum goes on the top. I want to get rid of moles of aluminum oxide. So here's my mole ratio for this one. I'm going to have 2 moles of aluminum oxide on the bottom. I get rid of, cross it out, so I take 13, multiply it by 4, divide it by 2, however you want to, you can simplify things and do it that way. I've got, excuse me, 3 sig figs, so it should be 26.0 moles of aluminum. And that's my answer. Okay, moles to moles, can do one step, moles of aluminum, done. All right, let's do one more. It says if we want the reaction to produce 28 moles of oxygen. Okay, so this time I know that I want to get, 28, not 28.0 moles of O2. We write O2 that way because of Hunkel-Fibber. It's found in pairs. We want to know the moles of aluminum oxide. Now it doesn't matter that I'm kind of in essence going backwards. It's asking me to predict the reactant. We actually do it the same way. And a lot of times, sometimes what I'll do is if this is what no, I'm lying. That's not the one that we want to do. We want to do oxygen. Let's try that again. No, not the highlighter. One more shot. Pen. Okay, we want oxygen. So another time, sometimes what I'll do is I'll go ahead and I'll write it. I want 28.0 mol, or I know 28.0 moles. I want to know the moles over here. So let's set it up. I got 28.0 moles of O2. Remember, I want to go 2 moles of aluminum. So I'm going to have 2 moles of aluminum oxide. I'm going to have 3 moles of oxygen. I do a bad job. Sometimes I put the S, sometimes I don't. I'm just going to admit that now. So, okay, so then on my math, I take 28, multiply it by 2. It's going to get me to be 56. I take 56 and I divide it by 3. And since I can have 3 significant figures in my answer, my final answer is going to be 18.7. It's out to be 18.66666, so I get 18.7 moles of aluminum oxide. Everything has to be labeled. Labeled, labeled, labeled. Okay? Alright, we're going to stop here, and then I'll do another video for the rest of this first section. Hope that helps.